Hello friends, welcome back. So we have now completed longitudinal static stability part for both wing alone and wing and tail combination. We have solved few example problems, how to figure out the neutral point for a given configuration, and then we also studied about static margin, which is positive for in order to achieve a statically stable flight, and then we have also demonstrated the wing and tail combination, right, in stable and unstable mode. So flight of wing and tail combination. Now let's proceed. So till now we are talking about an equilibrium condition, right? So what is an equilibrium condition? So we have the flight condition in which, or the state about which the resultant forces and moments are 0. So for a longitudinal case, what will be an equilibrium condition for longitudinal flight? So when lift is equals to weight and thrust is equals to drag and the pitching moment is equals to 0, which means half rho v square is Cm times C bar has to be 0. This implies the pitching moment coefficient has to be 0 for equilibrium condition. So we call, when the aircraft satisfies these three equations, then what we call is the aircraft or the UAV is said to be in trim condition, right? That means, what exactly trim means? We are maintaining a constant angle of attack, isn't it? So the aircraft is flying at a constant angle of attack where there is no resultant pitching moment acting, and then the lift is balanced by weight of the, like lift generated by the UAV is balancing the weight of the exactly balancing the weight of the configuration, and then thrust generated by the engine is satisfying the drag that is required by the system. Okay. So, okay, as far as a particular trim is concerned, that's fine. That means we are flying at a given angle of attack, right? So what if I want to change that angle of attack? Okay. So what I need to do when I have to fly at different angle of attack? So let's closely look at this equation. Lift is equals to weight, which is equals to half rho v square S times CL is equals to W, right? So when you're talking about a level flight, this particular parameter is constant at that particular altitude, and for a given UAV, say these parameters are constant, more or less constant. Okay, weight, we consider there is no change in the weight of the UAV due to fuel consumption. So when I have to fly at a particular velocity, I need to develop a particular CL from the wings. Right? How I develop that CL? CL as a linear function. We assumed a linear function of angle of attack, right? CL variation with angle of attack. So in order to change the CL, I need to change the angle of attack because CL naught is constant. You can't vary, right? And CL alpha you can't vary. It depends upon the profile of the aerofoil. Once you fixed it, then this is fixed. So the only variable that I have in my hand is alpha, right? So if I have to change the velocity, I need to change this angle of attack of flight, right? For example, say this is my reference axis or fuselage reference line, okay? FRL coinciding with my body axis, right? Say when there is forward velocity V infinity and say it is a level flight, that means this V infinity is horizontal, right? So this particular angle with respect to this V infinity is angle of attack alpha, and I have lift perpendicular to V infinity and weight acting. So this axis is perpendicular to fuselage reference line, or yeah, and weight is perpendicular to acting perpendicular to the local horizon. So W is the weight. So now when lift is balanced by the weight, you are flying at a particular velocity, right? So if I have to increase the velocity, let us say, if I want to fly faster, then I need to decrease the CL value to generate this weight, or to generate a force that can balance this weight. That means what I need to do, I need to change this angle of attack. I need to decrease this angle of attack. How can I decrease it? Or say if I have to decrease the velocity, I want to fly slower, then what I need to do is, I need to increase this CL value so that this equation is balanced. Right, still producing, so the force is still equal, produced from this lift, right, or the wings is still equivalent to the weight of the aircraft, of the UAV. Now, when I have to increase this, I need to change this angle of attack again. Say, I have to increase the angle of attack in this case. That means, I need to hold the aircraft at a particular orientation. See, when I say it is flying at a particular angle of attack, which means that the aircraft is oriented with respect to the flow at a at particular orientation, right? So, now when I have to increase the angle of attack, that means I need to change the orientation of the aircraft, and I have to hold that orientation, right? So, how can I do that? By means of a longitudinal control surface, right? So, we have a control surface which is located on the horizontal tail, right? Let us say there is a horizontal tail here. By deflecting a small surface which is attached to this horizontal tail, I will be able to either produce force upwards or downwards, right? So, with the help of this force that is produced aft the CG, right, aft CG, so say this is my CG, so this force multiplied this by this momentum will produce the corresponding moment that helps me to change this angle of attack, right? So, that means I need to, for each and every angle of attack, I need to produce different force at the tail, right? So, let us see what is that. So, what we are going to talk about is longitudinal control. Okay. So, how we achieve longitudinal control? With the help of elevator. So, let us get back to these equations again. So, when I have to increase the velocity, what does it mean? I need to produce the thrust which should be greater than the drag at that particular velocity, isn't it or not? So, say the engine is producing thrust T which is equals to drag, that is nothing but half rho v square S CD. So, this is equals to half rho v square S CD, right. So, initially say I am flying at 30 meters per second. Now, I want to change it to 40 meters per second. So, the initial engine setting or the throttle setting of my engine is producing only the force that is required to fly this at 30 meters per second. Right? Now, suddenly the force from the engine has increased, so that the engine output is higher compared to what it was initially. Okay? So, now with a higher throttle setting will be definitely more than the initial thrust. So, I have an excess force that will accelerate my aircraft to a desired new velocity. So, if I don't change my CL, if I still fly at a higher velocity, right? So, then I am producing additional force even in the perpendicular direction of flight, right? Here, in this direction. So, that will take the aircraft away from this level flight condition. The aircraft will not remain in the equilibrium, and then we can't claim that the aircraft is in trim, right? So, if you have to maintain the trim condition or say level flight condition, then what we need to do is we need to decrease this CL. Okay. So, immediately what is happening with the increase in velocity, there is a change in CL, there should be a change in CL. So, that we need to incorporate. So, how we are changing this CL? By changing the alpha. How this alpha is changed? With the help of elevator. Right? Let us see what exactly elevator is. So, elevator is a small control surface which is attached to the horizontal tail, right, for longitudinal control. So, which we have discussed earlier. So, let us say, as we discussed, the horizontal tail is fabricated or made out of symmetric aerofoil, right? Okay. So, let us say this is my fuselage reference line, or say let us say this is my chord line of this horizontal tail. Okay. Now, there is a small control surface and it's a part of the symmetric tail, right? So this particular portion which can be deflected, which is a part of this tail, can be deflected about a hinge point, right? So this particular portion can be deflected about this point up and down. Right? So this portion is known as elevator. Say, okay, so this is my horizontal tail, and this particular portion which is a part of this horizontal tail is called elevator, right? So this particular, and there is an axis about which this elevator can rotate. Right? So let us say if I hinge my elevator about this particular axis, so this axis is coming out of this board. So this elevator can rotate up and down about this particular axis. So this is known as hinge line of control surface. In this case it is hinge line of elevator control surface. So this particular portion is elevator. Okay. So this is horizontal tail. And as we discussed earlier, stretch your thumb along the positive axis of this hinge line, and the corresponding curl of your fingers will give you the positive rotation of the elevator. Okay. So now positive rotation of elevator is when the trailing edge of the elevator deflects downward. So this particular angle is delta E, elevator deflection. Okay. So this is positive when you deflect the elevator up, that is negative deflection. So a positive deflection, that means what is happening with the elevator deflection? So as we mentioned, this is my chord line, right? So let me draw it a bit clearer. So say this is my chord line, which in the earlier case is the line joining leading edge and the trailing edge, right? And which is nothing but the mean camber line as well, isn't it? For a symmetric airfoil, this is nothing but the mean camber line. Now when there is a deflection, what is happening? This chord line is up to this portion is fine, is same, but there is a change in the mean camber line here, right? So the mean camber is changing here. So when there is a change in mean camber line, that means there is change in, or the CL alpha of this aerofoil gets affected. Am I correct or not? So because of the change in the mean camber line, there is an upward force. The CL alpha is either increasing or decreasing. Let us say initially the aircraft is trimmed or flying at a particular V infinity, right? V infinity prime. This is horizontal tail, right? So it is, so the tail is seeing certain alpha t initially. Fine. So which includes both I of t as well, right? So let us assume that as stabilizer angle of attack, ST. Okay. So horizontal stabilizer and the corresponding angle seen by this horizontal stabilizer. So when there is no deflection, when there is zero deflection, the total angle of attack seen by this tail is equals to stabilizer angle of attack, just stabilizer angle of attack, which is equivalent to alpha minus epsilon plus I of t. This we discussed earlier, isn't it? But when there is a deflection with the elevator, what happens is, so in order to understand this properly, let us assume that the entire tail, horizontal tail itself is an elevator. Okay. So that means if I deflect this about a hinge line, right? So a elevator deflection will change the corresponding angle of attack. Am I correct or not? Let us assume a case where, so say this is my horizontal tail and the entire horizontal tail is my elevator. Okay. So this is my horizontal tail and the entire horizontal tail is elevator. I am rotating about certain hinge line, right? So now when I rotate this, what happens? So the airfoil still remains same. So this is like I am giving a delta here, which is actually changing the. So let us say this is my V infinity prime. So this is my initial alpha 1, alpha at tail 1, right? So this becomes alpha at tail 2, right? So the elevator deflection, when the elevator is the entire horizontal tail, it is actually affecting this angle of attack. That means you are actually changing the angle of attack with the elevator deflection. So there is an effect on the angle of attack due to elevator deflection, right? So that factor is generally given as, so the change in the angle of attack of the tail due to elevator deflection is given as tau, elevator effectiveness parameter. Okay. So even here in this case, that may not be explicitly visible, but still certain portion of the wing is being deflected, that is changing the local angle of attack, right? So that the change in the elevator angle of attack at the tail due to elevator deflection is given as tau, which is flap effectiveness parameter or control surface effectiveness parameter. So this, from the historical database, you will be able to figure out this parameter tau given the control surface area upon total lifting surface area. Okay. So if the elevator control surface is equals to the total tail area, let us say, that means it has to become 1. Tau has to become 1. Because change in elevator, let us say positive deflection is rotating it downwards, right? A degree of rotating it downwards is nothing but degree increase in the angle of attack. Just now we witnessed, right, in the previous figure. So that is when tau becomes 1. So it's not exactly a linear variation, right? So up to 0.8 when this is at 0.7. Okay. So we'll give you that data, how the elevator control surface area, if it changes, no, with respect to the total, if this ratio changes, how this tau changes. So it is fixed for a given aircraft, isn't it? Because you have a fixed control surface area and the fixed lifting area, tail lifting area. Right. So the total lifting area is nothing but the elevator area here. Or say, I'm sorry, the total lifting area is the horizontal tail area here. And so now when there is an elevator deflection, what happens is the lifting, the tail angle of attack will now be a function of this parameter tau times delta A. Okay. So this tau is nothing but, so alpha s plus dou alpha of tail d delta E times delta E. Fine. Where alpha of s is still 1 minus dou epsilon upon dou alpha times alpha plus I of t minus epsilon naught plus tau times delta E. Okay. This is the angle of attack at the tail when there is an elevator deflection. When delta E is 0, this becomes alpha s. This particular equation will be equal to alpha s. Now again coming back to this figure, when there is delta E deflection, there is change in camber, that means there is change in lift. Am I correct or not? So in a layman language, what we can see is it is trying to obstruct the flow here, So the flow will exert a force in the opposite direction. So now a positive elevator deflection, when the elevator is deflected downwards, there is an upward force at the tail, right? So this upward force is at the tail, lift at the tail. So say if I extend this, if I consider this as my fuselage reference line, FRL, right? And say the CG of the aircraft is somewhere here. This is my CG. Now the lift produced by this tail, right? So what effectively happening is a change in the pressure distribution because of the change in the control surface deflection. So the change in the pressure distribution is creating a change in the force at the tail, right? So that creates a moment about CG. So when there is a positive deflection, there is an upward force that creates a negative moment. So the change in the coefficient, or say the change in the pitching moment due to change in elevator control surface is less than 0, right? Negative. Or in other words, the Cm delta E is less than 0 here. Okay. So we'll see what is the Cm delta E. We'll discuss about that in detail here. So this Cm delta E is known as elevator control power. So elevator control power. How good you can control your aircraft using the elevator that is there depends upon this parameter Cm delta E. So higher the value, greater is your control. So higher the negative, greater is your control. Cm delta E is negative for a, is negative here, right? Cm delta E is less than 0. Now, when there is an elevator deflection, there is a change in total lift of the aircraft, isn't it? So delta L represents the total change in the lift of the aircraft, which is due to change in the lift at the tail, right? Am I correct or not? So this equals to half rho V prime square S of T, lift is, tail lift is due to tail lifting area, isn't it? S of T times CL, change in lift at the tail, lift coefficient at the tail, delta CL at tail. So this equals to delta CL of the total aircraft is half rho V prime square, V infinity prime square, ST divided by half rho V infinity square upon S is the wing reference area, because aircraft reference area is wing reference area. And then what you have is change in lift coefficient at the tail. So this change in lift coefficient at the tail is due to elevator deflection, right? Am I correct or not? So that is nothing but dCl upon d delta E at tail, right? So delta CL of the total aircraft is equals to eta times ST upon S, eta of horizontal tail, okay? Efficiency of horizontal tail times CL, change in the CL at tail due to delta E deflection, right? So what we observed, when there is change in delta E, there is change in camber, which in turn affects the CL alpha. Am I correct or not? When there is a change in camber, there is a change in lift curve slope. Am I correct or not? So this can be modeled as dCl upon d alpha of tail times the d alpha times d delta E. Right? So this is times delta E here. I'm sorry, please make a correction. There should be a delta E here. So this talks about change in lift coefficient for delta E deflection. Okay. Fine. So this is nothing but CL alpha of tail here. So now CL delta E of the total aircraft is equals to dCl upon d delta E, which is delta CL upon delta E is equals to, or delta E is nothing but delta E here. So is equals to eta ST upon S times, we know d alpha upon d delta E, d alpha of tail, d alpha of tail upon d delta E is nothing but tail effectiveness parameter tau, which we have discussed earlier. So tau times CL alpha of tail. Okay. So if you have the details about CL alpha of tail and tau, which means which can be deduced from if you have the details about geometric details about control surface area of the area of the control surface and the area of the horizontal tail. Taking the ratio of that, you will be able to figure out what is tau here, and then of course, once you have the details, you know what is St upon S, and knowing eta, you will be able to figure out what is CL delta E of this aircraft, right? Okay. So this is the CL delta E of the entire aircraft. So CL delta E, now the total CL of the aircraft, right, lift coefficient of the aircraft is due to CL naught, lift independent, like lift coefficient at 0 angle of attack, and its variation with angle of attack CL alpha into alpha, and then CL delta E into times delta E. So this particular CL delta E is what we have derived here, which is eta times St upon S times CL alpha of tail times tail effectiveness parameter tau. Okay. Fine. So initially it was just CL naught plus CL alpha into alpha when there is no delta E, but there is change, this delta CL here, delta CL is due to CL delta E times delta E here, where CL delta E is nothing but eta St upon S tau times CL alpha of tau. Okay. Similarly, there is a pitching moment, right? When there is change in the lift at the tail, there is a change in pitching moment. The change in pitching moment, apart from Cm of wing and tail combination. So when it is in trim, we know Cm is 0, right? So apart from that, so during that case, the contribution is only from Cm naught and Cm alpha. When there is a delta E deflection, there is a change in Cm total pitching moment, which is due to the lift produced at the tail, right? So the change in the pitching moment, delta M, is due to the lift produced at the tail, right, which contributes towards negative moment, let us assume. If there is a positive lift, there is a negative moment. So let us assume L of t is positive by convention. So this produces a negative moment, and the negative moment is because of lifted tail or change in the lift at the tail, right, times the distance between CG and the aerodynamic center of the tail, which is xCG or xAC of tail minus xCG, right? That's a moment arm, we know it. So or change in the lift of the aircraft, which is acting at the tail part. The change is near the tail, right? So or aerodynamic center of the tail multiplied by xAC of tail minus xCG. Right? So this equals to minus lift at the tail times xAC of tail minus xCG delta M. So this implies delta Cm, a change in the pitching moment of the total aircraft because of the elevator deflection, is due to the change in the lift at the tail because of the elevator deflection, which is equals to eta St upon S times. So this particular parameter is called L of t, length of tail, upon C bar times change in the lift coefficient at the tail. Okay. So we know that change in the lift coefficient at the tail, this change in the pitching moment coefficient is equals to minus eta VH, right? VH is the tail volume ratio. This particular product is the tail volume ratio. Area of the tail times length of tail upon area of the wing times mean aerodynamic quarter of wing. So this particular product is a tail volume ratio, VH, and delta CL at the tail is due to change in lift coefficient at the tail, right? This is delta CL at the tail, this particular parameter. So you can simply substitute it there. Right? So this is nothing but CL alpha of tail times eta. Okay. So times delta E, of course, eta times delta E. So the total pitching moment or change in pitching moment coefficient of the aircraft due to delta E deflection is equals to minus eta VH CL alpha of tail times tail effectiveness parameter. Okay. So the Cm delta E is equals to Cm delta E is equals to minus eta VH CL alpha of tail times tail effectiveness parameter. So this is one equation and this is the other equation that talks about CL delta E and CM delta E. Okay. Similar to this, the total pitching moment of the aircraft is now can be expressed as Cm naught plus Cm alpha into alpha and Cm delta E times delta E. So when you just have wing and tail combination, right, what you have is Cm naught plus Cm alpha into alpha when there is no elevator deflection. But when there is an elevator deflection, we have additional terms Cm delta E, that elevator control power comes into the picture, times delta E. Okay. And what is Cm delta E? Cm delta E is equals to, so earlier we discussed Cm delta E has to be negative, isn't it? Whether it is true or not, eta is positive, we know, tail volume ratio is positive, CL alpha of tail is positive and tau we witnessed it is positive. So this entire positive term multiplied by minus, what we have is Cm delta E as negative. Okay. Now you have Cm naught, Cm alpha, Cm delta E, and similarly for trim conditions, before talking about trim, we have CL naught plus CL alpha into alpha and CL delta E into delta E in the linear regime, right? This is what we have modeled, right? So we have come up with this aerodynamic model for the linear regime, which is a function of alpha as well as delta E for both the equations. Now we are talking about how to change angle of attack from one trim condition to the other trim condition. Or let us say if I want to trim the angle of it, trim aircraft at certain angle of attack, what should be the corresponding elevator angle, elevator deflection that I require, or trim or the elevator deflection to trim the aircraft at that particular alpha trim. Okay. That means we witnessed for trim Cm is 0, right? So if you substitute that there, what I have is Cm naught plus Cm alpha times alpha trim plus Cm delta E times delta E trim. Okay. Similarly, CL is equals to CL, this CL becomes CL trim. Okay. CL trim is equals to, how can we estimate CL trim? From the level flight equation, L is equals to W. From L is equals to W, when you want to fly at a particular velocity, then you will be able to find out what is the corresponding CL trim. If you know that CL trim, you will be able to find out what will be the resulting alpha trim and delta E trim to fly at that particular velocity. Right? That can that satisfies the level flight condition. Okay. So this is equals to CL naught plus CL alpha times alpha trim plus Cm delta E times delta E trim. Okay. Say this is my equation 1 and this is my equation 2. Okay. So I have two equations. See, Cm is 0 here and we know CL trim. So how can we find CL trim? So from lift is equals to weight. Okay. So CL trim is equals to twice the wing loading upon rho times V infinity square or V trim square, velocity for that particular trim condition, V trim square. So given the data about this and the flight velocity that you want to fly, you can find out what is the corresponding trim CL, lift coefficient that you require. So for this lift coefficient, what should be the alpha trim and delta E trim? So you have two equations, that means left side is known here, right? And you have two unknowns here in these two equations. You can simply solve it, isn't it? You can solve for what is alpha trim and delta E trim. Can you do that? So say 1 multiplied by, so if I want to find out delta E trim in the first place, 1 multiplied by CL alpha minus 2 equation 2 multiplied by Cm alpha, right? So this implies delta E trim. So what I am doing, I am multiplying this equation 1 with CL alpha, right, and then equation 2 with Cm alpha and subtracting 2 from 1, okay. So that this alpha trim terms gets cancelled out, I have this equation with one variable, and I can rearrange the terms so that I can get to know what is delta E trim. Okay. So this delta E trim is equals to Cm delta E times Cl alpha, or say Cl alpha times Cl delta E, Cm delta E minus Cm alpha times Cm alpha times Cm delta E. This is a mistake. This is Cl delta E. Okay. So please correct this equation. So this is Cl delta E. That's the reason why. So this is Cm alpha times Cl delta E. This equals to, so minus of Cl trim times Cm alpha, Cl trim times Cm alpha, minus Cl naught times Cm alpha, Cl naught times Cm alpha. Okay. So delta E trim is equals to minus of Cl trim Cm alpha plus Cm naught Cl alpha minus Cl naught Cm alpha upon this, like you can say Cm delta E, right? So Cm, this is like Cm alpha, Cm delta E, Cl alpha, Cl delta E. So you can take the discriminant of it. So in that case, this minus will not be there. Okay? Fine. So similarly, what is this? Cm alpha, Cl delta E minus Cl alpha, Cm delta E. Okay. Similarly, alpha trim, in order to find out alpha trim, equation 1 multiplied by Cl delta E minus equation 2 multiplied by Cm delta E. So if I do that, what I have is, so alpha trim is Cm alpha times Cl delta E minus Cl alpha times Cm delta E is equals to minus Cl naught times Cm delta E minus Cm naught times Cl delta E, right, plus Cl naught times Cm delta E. Okay. This equals to alpha trim is equals to minus of Cl trim. Oh, this is I'm sorry, this is Cl trim, not Cl naught. This is Cl trim, right? Cl trim multiplied by Cm delta E here. So Cl trim multiplied by Cm delta E. So plus Cm naught Cl delta E minus Cl naught Cm delta upon, you can find the determinant Cm alpha, Cm delta E, Cl alpha, Cl delta E. Okay. Fine. So with these two equations, you can find out what is delta E trim and alpha trim. So we now got delta E trim, or say what should be the alpha trim and delta E trim if you want to fly at this particular Cl trim condition, right, which corresponds to the velocity V infinity for a given UAV. Right. So when you want to change from one velocity to the other velocity, you need to change the Cl trim. The Cl trim changes which can be achieved by elevator control. Right? How the CL can be changed? By changing the alpha trim, which is achieved from elevator trim. Right? So let's look at what we have done till now. So this particular equation the Cm equation, which is Cm naught plus Cm alpha into alpha plus Cm delta E times delta E, right? So what should be the control surface deflection to trim this particular aircraft? Delta E trim. So in this, the Cm naught again, see we have wing and we have a tail combination, and in the tail we have an elevator right now. Okay, so this Cm naught will still remain the same, like Cm naught is equals to Cm AC of wing plus CL naught of wing times x bar CG minus x bar AC of wing minus eta St upon S, or you can say VH tail volume ratio, VH times CL alpha of tail times I of T minus epsilon naught. Okay. So this still remains the same, and the Cm alpha that we are using in this equation is CL alpha of wing times xCg minus x AC bar of wing, right, minus eta VH tail volume ratio, which is St upon S times LT x bar AC of tail minus x bar CG upon, right, yeah, x bar CG, that particular product is a tail volume ratio, ST LT upon SC bar. Okay. So tail volume ratio multiplied by CL alpha of tail multiplied 1 minus 2 epsilon upon dou alpha, change in the downwash due to angle of attack, change in angle of attack. Okay. So these two, Cm naught, Cm alpha still remain same, and Cm delta E we derived, right? We just derived before solving for this alpha trim and delta E trim, which is minus eta tail volume ratio times CL alpha of tail times eta. Okay. So Cm delta E is negative for a statically stable aircraft, Cm naught is positive and Cm alpha is negative, right? So now for trim condition, so we will now see what will be the change in the trim angle of attack with the change in the trim lift coefficient. So when I have to fly at different velocities, I need to change my trim lift coefficient, right? That's what we discussed. So what will be the change in the trim elevator deflection, or what should be the change in elevator deflection when there is a change in trim lift coefficient? Okay, let's derive that. So for trim, there is a reason to derive it. We'll soon discuss about that. So for trim, Cm has to be 0. So substituting 0 in this equation, delta E trim is equals to minus Cm naught minus, or say minus Cm alpha times alpha trim upon Cm delta E upon Cm, so enter Cm delta E. Am I correct? So just substituting Cm is equals to 0 in this equation and trying to find out what is delta E trim. So delta E trim is equals to minus of Cm naught upon Cm delta E, okay, minus of this Cm alpha upon CL alpha of the entire aircraft times CL alpha times alpha trim upon Cm delta E. Okay. So delta E trim is equals to minus Cm naught upon Cm delta E times dCm upon dCl, right? So Cm alpha upon CL alpha is dCm upon dCl, right? So multiplied by, let us assume the total trim angle of attack is dominated by CL alpha times alpha trim. Okay. So let's have that assumption. Then what we have is, this is nothing but CL trim upon Cm delta I. Okay. So what is dCm by upon dCl? This is nothing but negative of static margin, right? Do you remember this? So delta E trim is equals to minus Cm naught upon Cm delta E plus x bar Np minus x bar Cg upon Cm delta E times Cl trim. Since here assume CL of total aircraft is dominated by CL alpha of the aircraft times alpha trim. Okay. Assume CL naught is very small. Okay. Since dCm upon dCl is equals to minus of static margin, okay, which is minus of x bar Np minus x bar Cg of the aircraft. So just refer our previous lectures, you will be able to figure out this. And now, so can I express this delta E trim like this in this form? So delta E naught plus change in delta E due to change in CL trim condition. Okay. Change in CL trim. When there is change in CL trim, there is a change in delta E trim. Okay. Times delta times CL trim. Okay, is equals to minus of Cm naught upon Cm delta E plus x bar Np minus x bar Cg upon Cm delta E times CL trim. Okay. So by comparing the constants and coefficients of CL trim, what I have is delta E naught is equals to delta E naught is equals to minus Cm naught upon Cm delta E, okay, and d delta E upon d CL for trim, right, is equals to change in delta E for change in CL trim, okay, is equals to minus of x bar Np minus x bar Cg, x bar Np minus x bar Cg upon my Cm delta I. Okay. So there is a lot to learn from these equations. So the elevator deflection delta E naught mainly governs when, like, is required when your Cg has to is at the neutral point. Am I correct or not? If your Cg is at the neutral point, so that means you don't have this trim coefficient anymore here. So you need to satisfy this delta E naught for this Cm naught and Cm delta E. So we know Cm naught is positive for a statically stable aircraft and Cm delta E is negative. So this particular delta E naught becomes positive, right? So this is how the variation of Cm with delta E variation of CL and delta E, right? So delta E is positive here and delta E is negative, and this is 0. Okay. So what is delta E positive? We just discussed about it. Deflecting elevator downwards, right, is delta E positive, which gives a negative moment that decreases angle of attack, that decreases your CL. It has to be, isn't it? That's why if you see this particular equation, dou delta E upon dou CL trim, so when there is, for a positively or for an aircraft or a UAV with positive static stability or static margin, you have XNP minus XCG is positive, right? So Cm delta E is negative. So this particular slope is negative. So when there is a positive or downward deflection in elevator deflection, so the trim that results, the CL trim that's going to result is negative or decreased, or when there is a positive increase in delta E, there is an increase in CL trim, or say when you have to decrease your CL trim, you have to increase that delta E or deflect your elevator downwards. Okay. So that means the slope is negative for this plot. If I have to plot delta E versus CL here, right? CL trim. If I have to plot delta E versus CL trim, this particular equation, this is nothing but is equals to delta E, right? This is delta E trim, right? So delta E naught plus slope times CL trim, isn't it? Slope is negative here and delta E is positive. So that means delta E naught is positive. Let us say this is my delta E naught, right? So this is positive, and for a given CG location, for the same UAV, for a given CG location, that means that you have placed the weights and distributed the weight, all other components in such a way that you achieve at this particular, the CG will result in this XCG, right? For that particular CG location, so this XNP minus XCG upon CM delta E is negative, right? For that CG location, the slope is negative here, for example. So delta E naught corresponds to what? If XCG is at XNP, XCG is equals to XNP, neutrally stable condition. Okay. And now when there is when the CG is ahead of the neutral point, right? What does it mean? If XCG minus XNP minus XCG is positive, what does it mean? For example, if this is my aircraft, okay? Let us say this is my aircraft. Okay, so wing alone aircraft, say this is my reference line. So say this is my NP, right, neutral point. Now if it has to be positive, that means this distance XNP, this is XNP, should be greater than this CG, distance CG. Say this is my CG distance. So this should be greater than, otherwise the CG should lie ahead of the XNP, right, close to the leading edge here, let us say. Now, so for this particular location of CG, I have this slope constant, isn't it? The slope is constant. Okay. Let us say this particular line represents XCG1 position. Okay, XCG1. Now consider a second location. So what can I do for that is, this corresponds to XCG XNP. Okay, so say this is my reference line. So this is my NP neutral point. Okay. Now this is my XCG1 location 1. Okay. So say I have an aircraft, or a wing alone aircraft, something like this. Okay. This is my XCG1. Now, let us say I take my CG a bit more or forward to, or towards the leading edge here, right? Towards the nose of this aircraft. Okay. So this is, let us say this is my XCG2. Okay. So that means the distance between this neutral point and CG location is increased, which makes this slope more steeper, isn't it? That is more negative here. Am I get it or not? So this makes the slope more negative. And delta E naught is independent of this location of center of gravity, isn't it? That is what we figured it out here. Okay. And then let us assume the third case where this is like XCG2. Okay. Now let us assume another case where the CG is more further up, further towards the nose. This is XCG3 location. So that means it's more steeper now compared to the previous case. So what I have is this particular slope. Let us say this corresponds to XCG3. So how far I can move this? Question is how far I can move this. Let us consider there is another location XCG4. Okay. So let that be XCG4. Okay. So what do you mean by this? I am changing CL trim here, isn't it? The CL trim, or what is the CL trim? I am changing the CL value, right? Isn't it? So at each and every, when there is a change in elevator deflection, that means for each and every CL there is a particular delta E value, which means there is a particular alpha trim. Am I correct or not? So if for the same CG, if I take some other CL value, so there is a particular delta E negative here in this case, in this particular case. If I have to achieve this particular CL value, then I have to give delta E positive here. Okay. So this is what this curve talks about, isn't it? Am I correct or not? And if you might have noticed that at CL trim, or say if this is your desired CL, let us say this is called design CL, where there is no need of delta E trim, right? Delta E should be 0. You should be able to achieve this CL trim, CL design, right? CL design without any control surface deflection, right? So that CL design, yeah, corresponds to a particular CG location. So corresponds to a particular curve here. Am I correct? So yeah, coming back to this. Now let us say there is CL maximum. Okay. There for any aircraft, or we know we have CL maximum for the wing, right? So how can I achieve CL maximum? It is again at a particular angle of attack. Am I correct or not? Am I correct? So how can I achieve that angle of attack? By deflecting the control surface, right? So that means a negative deflection will give me positive angle of attack. What is negative deflection? So deflecting elevator upwards will produce a downward force that creates a positive moment which increases the angle of attack, right? So if I have CL max is at higher angle of attacks, or say angles of attack, higher positive angles of attack. So that it is clear that I need a negative deflection here, right? So there is a maximum negative deflection for the elevator, isn't it or not? So let us say if this is my symmetric aerofoil, I may not be able to deflect it 90 degrees down. So apart from the mechanical constraints, I am talking about aerodynamic constraints. The flow may separate altogether. Right? So there is certain value of this control surface deflection where the flow is still effective on the control surface. Right? So that particular value is known as delta E max. So let us say this is my delta E maximum. Right? Negative delta E max, or maximum upward deflection of the elevator. Right? So with this delta E max, I will be able to achieve CL max. Let us assume that. Okay? So this delta E deflection up and downward, right? Otherwise upward maximum deflection will achieve alpha maximum or alpha stall. Okay? With which I can achieve this CL maximum. Okay? Now the CG location, as the CG location varies, the slope is changing here. Right? So now if I look at this particular curve, right, CG4, I may not be able to achieve with maximum delta E deflection, I may not be able to achieve this CL maximum, because CL maximum is somewhere here. Am I correct or not? I am not able to trim my aircraft at CL maximum. I have to satisfy myself with this particular, like with the limited regime of CL. I may not be able to use the entire CL versus alpha that my wing possesses. Do you understand? So if you take it more forward, right? So this is a constraint that you face. You can't be able to use the CL, total CL available. So now say, if I take this CG a bit backward, right? From here I shifted my CG here. So that means I am able to increase, yeah. Still I am not able to achieve this CL maximum. Right? I am able to, right, yeah, increase the available CL regime, but I am still not able to achieve the CL maximum. Right? Now say I have taken my CG further backward. So with this, I am able to do this, right? Do you get this point or not? So I don't need this delta E maximum here. For example, with this delta E maximum, I can achieve something else here, more than CL max. I don't even require delta E maximum if my CG is within this limit, right? So for this particular curve, yellow, orange curve or CG1 location, I just need some negative delta E to achieve that CL maximum, some upward deflection, that's it. Okay. So now the constraint on the forward CG location, the most forward CG location is from this delta E maximum condition. Right. So the elevator control surface with which, or the elevator control deflection with which you still be able to trim your aircraft at CL maximum. So the CG location for which with the maximum elevator deflection, upward elevator deflection, you can still be able to trim your aircraft at CL maximum. Right. So that is the most forward CG location. So by substituting that in this particular equation, right, so what is this XNP minus XCG most forward, this becomes CL trim becomes CL maximum, right. So delta E becomes delta E maximum. Okay. By substituting those parameters in this equation, we will be able to find out what is the most forward CG location. Okay. How can I do that? So I have delta E max. Delta E max here is maximum upward deflection, right, negative deflection, is equals to delta E naught, right, plus x bar NP minus x bar CGF. CGF talks about most forward CG location, okay. CGF upon Cm delta E times CL max. Now you are trimming your aircraft at maximum CL. Okay. So by rearranging this equation, so what I have is XCG, most forward CG location, is equals to x bar NP minus delta E max, delta E naught multiplied by Cm delta E upon CL maximum. So you can't simply place your CG far ahead. No? If you want to still want a control, good control of your aircraft, you have to limit your CG forward location, right? So what we have is a permissible. Now with this details, what I can say is, so if I have an aircraft, something like this, okay. Say if this is my reference line, say this point as my neutral point, okay, and this is my XCG most forward, which is governed by this delta E maximum, right. So this particular distance is the allowable CG traverse. You have to design your UAV to lie within this particular distance, right? The CG of the UAV should be within this limits, X. So the most aft location is XNP. So see, we are not talking about stick fixed and stick free condition, because in a UAV there is no point of stick free. It is always controlled by a servo motor, right, or an actuator. So this CG, so this is nothing but the most aft location of a, see this is XNP, corresponding location is, most aft location is the neutral point for static stability, and most forward location is XCGF, which is governed by this delta E max. Okay. So we have now covered good enough concepts in order to talk about performance analysis, right. We will consider a UAV, data of a UAV, and then we will do performance analysis for various. So for example, if I have to trim that aircraft at different angles of attack, right, within the linear regime, let us say, at different angles of attack, what should be the corresponding delta E trim, right? For a alpha trim, what should be delta E trim, and then say what should be the velocity of the flight resulting from that, and then what should be the thrust required, power required, and also CL by CD and CL power 3 by 2 by CD for that particular configuration, how they vary with velocity or say angle of attack. That's what we'll solve using an iterative approach. So I wish you should, like one of our TA Kazi made a tutorial on MATLAB. So you can start using, you start getting comfortable with the MATLAB environment. So we'll be solving that problem using MATLAB, fine? The iterative problem using MATLAB. Thank you.